Alright folks, we're going to talk about dilations. Here it says if the dilation is occurring about or with respect to the origin. Those are two different phrases you're going to say. They'll say a dilation about the origin, or they'll say that with the phrase with respect to the origin. Then all you have to do is apply the scale factor to each ordered pair, and it will effectively shrink or enlarge the image. So if the scale factor is greater than 1, it's going to be an enlargement. Okay, obviously through multiplication. Multiplying by a number greater than 1 increases your product. If the number is between 0 and 1, it will shrink it. Okay, if it's negative, between 0 and -1, it'll still be a shrink, but it also provides a reflection, ultimately 180-degree rotation around the center of origin. So, to be honest, we're not going to do a whole lot of that. I might show you an image where we have a negative dilation or negative scale factor, but for the most part they're going to be positive. Let's first talk about the notation. You're going to see capital D for dilation, and then there's going to be a subscript. So let's say we put a 3 there, and that 3 is ultimately your scale factor. Okay. This is not, dilations are not isometries or rigid motions. Remember, within those things, within isometries or rigid motions, distance was preserved, distance was saved, it did not change. With a dilation, that's the main goal, is to change distances. And what happens with a dilation is that we end up with two shapes. The image and the pre-image should be similar to one another. So we've got a lot of stuff going back to chapter 7 here that is actually going to be present. So we'll just do an example here real quick, an easy example. We've got this one here. We're going to see, I'm going to call this point A, and it's located at 2, 3. B is located at 1, -1, and C at -3, 1. And what you're going to see them say is something like this. They'll say dilate scale factor of 3 of the figure ABC. What I'm going to do is I'm going to actually take, this is usually how I do it, I'm going to write my ordered pairs down. So A was 2, 3, B was 1, -1, and C -3, 1. And each one of these is going to get multiplied by 3. So I write times 3, times 3, times 3, and that's going to generate A prime, which all we have to do is multiply each coordinate by 3. So it's going to be 6, 9. B prime is going to be at 3, -3, and C prime will be at -9, +3. Now if I plot those, so 6, 9, so 1, 2, 3, 4, 5, 6, and then 9 is right there, so there's A prime. B prime is at 3, -3, so 3, -3, there's B prime. And C prime will be at -9, 3. So there's C prime. And what happens then if we connect these? Let's do it this way. So that's that, and our final one. And what's interesting about a dilation, to make sure that you've done this correctly, one thing to know is that if I go from A prime back to A and then back to the origin, there is going to be a line that connects those three. Okay, there is going to be one singular line that goes from B prime to B back to the origin. So if we go do that, and then there's going to be another one that goes from C prime back through C back to the origin. So if you were to draw a segment or a ray or a line or whatever, after the dilation, they all go back to the origin, and they will pass through the image and pre-image's vertices. So that's kind of an interesting fact. And the reason for that, the logic for that is essentially when we do this, when we multiply by 3, we're not only changing the distance by a factor of 3, but remember distance is very closely tied to slope, okay? Because if I want to find, let's say, the distance from the origin to A, okay, so that little distance right there, remember what the distance formula does is it first finds that distance, which we would refer to as our run, that distance, which we call our rise, and we divide those, or sorry, not divide those, we square both those, add them together, and take the square root, it gives us this, okay? But that's also the slope. If we were to take the difference of the x's divided by the differences, or sorry, the difference of the y's and divide it by the difference of the x's, that would give us the slope. So there's a very close intertwining of distance formula and slope formula. But if we look at this, think about that rise over run. Okay, the rise over run was 2 and 3. Okay, if I go from the origin to A prime, that run, there's 2, 3, 4, 5, 6. And if I count that, that rise is 9. So we had a run of 6 and a rise of 9 from the origin to A prime. Well, if I look at that 2 compared to that 6, it's a factor of 3 that is the difference. If I look at that 3 and that 9, it's a factor of 3, that's the difference. So that's one way of kind of realizing what's happening and recognizing the relationships in a dilation. Obviously, if all they ask you for the ordered pairs and a plot it and the graph and all that kind of stuff, this is the route you go. Pretty easy algebraically. What is more difficult is to dilate around a point other than the origin. Okay, so we'll go ahead and do an example of that. First thing I want to do is identify what these coordinates are for this shape. So I'll say A is located at 2, -1. B is at 3, -3. And C is at -4, -2. Okay, and it wants us not to rotate or dilate around the origin, but to dilate about the point 2, 3. So I want to use this point here as my dilation point. Okay. Now that's kind of like what we did with rotations. Our dilation factor of 2 is only true and only used, we can only multiply the ordered pairs if we're doing this around the origin. Well, this is not the origin. Okay, so what we did up here for this problem does not work for this problem. So what we have to do is we have to tell the problem essentially that that point is really 0, 0, and then relist or relabel everything off of that being 0, 0. So I'll recall this point 0, 0, and now I have to figure out what would this order pair for A be. Well, if I count from here, obviously x distance would be 0, and then 1, 2, 3, 4, so down 4. Okay, so that's what the A would be. Okay, 0, -4. Let me use a darker blue. 0, -4. Okay, so you can kind of maybe see how you could have gotten that 0 by taking 2 minus 2, and you could have gotten the -4 by taking -1 minus that 3. Okay, so same thing, I could take this 3 minus that 2, and it would give me 1, and now take this negative 3 minus that 3, and it'll give me negative 6, and that will be the new B coordinate. And I can count as well from here, go to the right one, and then down 1, 2, 3, 4, 5, 6, and you can see 1, negative 6. So here at C then, I'll take negative 4 minus that 2, so negative 6, and then negative 2 minus that 3 would give me negative 5. Again, to verify that, go from here, left 1, 2, 3, 4, 5, 6, and then down 1, 2, 3, 4, 5. So now these blue points are actually the points that we can dilate around by a factor of 2. Okay, so I'm going to say dilate by a factor of 2, and that's going to say, okay, A, which was at now 0, negative 4, that's going to dilate to, I'm going to call A prime real quick, and it's going to be 0, negative 8 when I double. B, which was at 1, negative 6, is going to produce the point, when I double that, it's going to be 2, negative 12. And then C is going to be double that, so it's going to be negative 12. Oh, let's go ahead and write negative 6 comma 5 first. Negative 5. When I double that, it's going to give me negative 12, negative 10. Okay, so now you could, let's just go with this one here. Actually, let's do that one first. If I were to just go from 0 right here, and it's saying go to the right 2, 1, 2, and then down 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12 would be maybe right there. Okay, so that would be the point, negative 12, negative 10, off of that 0, 0. Okay, but remember, the problem does not know we put these red axes here. It doesn't know that we're really relabeling everything as 2, comma 3. So when I want my final answer of B prime, it's not from here. It's not 2 to the right and 12 down from there, but it's whatever it is from 0, 0, the true origin. I'm going to go over 1, 2, 3, 4, and then down 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's to the right 4 and down 9. And let's just think about how we can get that number there, or that ordered pair, from what we started with here. Remember, we took 3 and removed 2 from it to get this 1. We took this negative 3 and removed 3 from it to get that negative 6. So now let's add those back in. Okay, so I'm going to add back in a 2 to that point. So it'll give me 2 plus 2 is now that 4. And I'll add back in 3 to that coordinate, and it'll give me my negative 9. Okay, so what I'm going to do here to find A prime then is the same thing. Add back in 2 there, and then add back in 3 to that. Basically, and this is the same thing we did with rotations, you're going to add back in whatever you removed. So I'm going to add back in 2, so it gives me 2. And I'll add back in 3, so it gives me negative 5. And then C prime, add back in 2, so it would be negative 10. And then add back in 3, so it gives you negative 7. This then is going to be the image that we get when we dilate this thing around the 0.23. Use GeoGebra here real quick to kind of confirm this with you, so you can see some relationships maybe a little bit better than my drawing. So A then is located at 2, negative 1. B was at 3, negative 3. And C was at negative 4, negative 2. Alright, so I'm going to connect those, create my polygons. So that's the image we started with. Now I'm going to create a slider here with my increments of 1. And what I'm going to do, I'm going to ask this thing to dilate. So it's, I actually got to put the point, what do we use, 2, 3? Yeah. I'm going to put the point 2, 3 in here. So that's my point of dilation. And now we'll dilate this. So we click P, and then I want to select that object. I guess I can't maybe do it that way. So let's just go select object. Okay, I did it backwards. Select object, then the point P. There we go. So then I'm going to use a scale factor of D here so I can actually change it a little bit. So if I put a scale factor of 1, right, it obviously doesn't change anything. We have a scale factor of 2. So when we have a scale factor of 2, we get obviously an enlargement. Okay. But now let's look at A prime. A prime was at 2, -5. Is that what we came up with here? 2, -5. B prime was at 4, -9. And C prime is at -10, -7. Something to look at and visualize here is if we were to take a ray from B prime back to B, notice it passes through P. A prime back to A also passes through P, and C prime back to C also passes through P. And that's the feature of dilations, is when you connect corresponding vertices, we get that segment to go through the center of dilation. Something to think about. I think I can do this a little bit, but just to show you that those angles there at C are the same, the angles at A are the same, and the angles at B and B prime are the same. So what's that tell us about these two triangles? Is that they're always similar. Okay, they're similar by angle. Therefore, if I take CB's length and divide it by C prime B prime's length, we get 1/2, which is what we should expect if our dilation factor was 2. I'm comparing the small one to the big one. And then AC divided by A prime C prime, again, is 1/2. And then AB divided by A prime B prime, again, is my 1/2. If I would change the scale factor to 3, obviously then you can see that now it's a 1-to-3 relationship. I would get the 3 here if I would compare them, the big one to the small one, obviously. Kind of show you what happens when we have a scale factor of 0 basically just means that all our points go to 0, 0. That's not really that interesting. Or I guess not. They go to the dilation point. So all these points A prime, B prime, C prime, you see they all became 2, 3. They go to the point of dilation. Now if I go a negative, you see there that there's a rotation happening here. And you don't have to do any of this, but let's just look at that right there. I think you can see that from A to A prime, there's a 180-degree rotation of A. If I go from put a circle at there, and I go from B to B prime, there's a 180-degree rotation. And then the same thing happens for C. Oh, I did that wrong. C to C prime, there's a 180-degree rotation from those two. And because there's this negative aspect, there's some flipping of the object that happens. Excuse me. And that we'll spend more time in Algebra 2 and college algebra talking about that negative and how it creates a reflection in a particular plane, essentially. Let's see here. I think when you're doing these, it makes sense. Just right, because I think some of you had some questions about the rotations and how we do that. Kind of if I gave you 3 points or 1 point or 2 points, the actual process of counting from this original origin, or so this fake origin or pseudo origin to these points, and labeling is not that hard like we did here in blue. That's not that difficult. And then plotting essentially these off of that point there isn't that hard. But then to get these, we obviously can go back to this 0, 0 and count to get those points. That's not something we can't do. But if I had, 10, 15, 20 different points that I was asking you to do this with, you would not want to go along that route or that process. So I'll give you a shortcut here, and it's what we did here. Okay, so first thing you're going to do is you're going to do this in columns here. So like we did here with A, B, and C. So this was our these were our original points. Actually, no, they were not. They were. So let's do it this way. So our originals were, so A was 2, -1. B was 3, -3. C was -4, -2. So these were our originals. Okay. Then to get these, we subtracted. So this would have been we took the original point minus, so these became original minus point of dilation. Okay. These then were to actually, these were created here by actually then dilating. Oh, spell it right. Dilating what you found there. Okay, so in the previous ordered pairs, that's when you actually dilate. Okay, and then these were these were our final ones. These were by taking the previous ordered pair. So that was after dilation. Okay, and now you're going to add back in the point of dilation. Okay, so let's do a practice one here with that process here. Okay, so I'm going to write again our original. Let's go. This here would be our original minus point of dilation. This column will be then dilated. Okay, so that's when we're actually going to apply the scale factor. Okay, and then this last one will be then the dilated plus point of dilation. So it's adding back in what we subtracted right here. So, and I don't care what. Let's take let's for example, let's say we're going to dilate around. Let's go to dilate by a scale factor of 3. Let's go the point. I'll do a series of points here, but let's dilate around the point called P, our point of dilation. Let's call it I don't know, 5, 7. All right, so I'll just start with a series of points here. Let's do it with 2, 3. Let's do it with -5, 13. And let's go to -7. Okay, just some random points here. So what we're going to do is we're going to take, I'll just call these A, B, and C. So we're talking about these here. I'm going to take point A, and I'm going to subtract away the point of dilation. So I'm going to take 2 and remove that 5. So it's going to give me -3. I'll take 3 and remove that 7. So it gives me -4. Do the same thing down here. So -5 minus that 5 be -10. This is kind of how I like to do all my x's at once. So I'll take 2 minus that 5 gives me -3. And now I do all my y's. So 13 minus 7 will give me 6, and -7 minus 7 gives me 14. Now we're actually going to do our scale factor. So this is the time that we're going to actually multiply by 3. So we take the previous point and multiply by 3. So it gives me negative 9, negative 12. This is going to be negative 30, 18. And this one's going to be negative 9, negative 42. And then we are going to add back in. And this will give me my final image. Final image is to add back in what we subtracted out. So what we subtracted out, remember that 5 7. So I'm going to take negative 9 and add back in 5. So give me a negative 4. I'm just going to do all my x's. So negative 30, add back in that 5, gives me negative 25. And then negative 9, add back in that 5, gives me negative 4. And now do the same thing with your y's. So negative 12, add back in the 7, gives me negative 5. 18, add back in the 7, gives you 25. And then negative 42, add back in the 7, gives you negative 35. So let's go through and use GeoGebra to see if what we did makes sense, if it all pans out. So we'll start with a blank one here. So we had A was 2, 3, B was negative 5, 13, C was 2, negative 7. Point of dilation was what, 5 7. Okay, so I'm going to take these 3 points and dilate them by a factor of 3. So those 3 points off of that factor of 3. Let's see what the ordered pairs are. A prime, B prime. So A prime we said was negative 4, negative 5. We got that. B prime we said negative 25, positive 25. We got that. And C prime negative 4, comma negative 35. We've got that. One thing to think about again: does P? We go B prime to B through P, or we start at P and go to B, and we see then that passes through B prime. P to A passes through A prime. P to C. Now I can't see C prime here, but I guarantee you that when I zoom down or scroll down, you're going to see C prime on that ray, and there it is. So that's one thing that you might actually kind of come encounter with is I'll give you a question that asks you, can you come up with the location of the point of dilation without knowing it? For instance, so this is kind of what I'm talking about. If I give you, let's say, that figure there, and I'm going to pause this. I'm going to actually dilate this and then hide the point to you so you can't see it. We'll come back. Quiet. Okay, so what we see here is I've got set up a. I started with this pre-image, and this is now the image. Okay, so I've dilated it. Maybe here in a little bit I'll ask you what the scale factor is. Yeah, turn lights on. But if I ask you the point of dilation, we know the point of dilation is going to be on that ray somewhere. Okay, because we took from A prime to A, and we pass through, and they will go through the point of dilation. Now, that doesn't provide us really any use. It took the entire plane, the entire XY plane, and now narrowed it down, which is a lot of coordinates, and it narrowed down to all the coordinates that are now on that black line. It took an infinite number of points, and it dwindled it down to another set of an infinite number of points, but it's a still smaller set of infinity than what we started with. So now the same thing should happen. We should have, if I go from C prime to C, C prime to C, then somewhere on that line is the point of dilation as well. Well, if the point of dilation is on that line and it's on that line, then right there is the point of dilation. Now the next thing I might ask you is, what was actually the scale factor? Algebraically, what you would have to do is you would have to find the distance of some respective segments here. So you may have to use the distance formula with this point. So this point's at 12.8. This point here is at 20, -12. This point here at A is at 4.6. And this one here at B is at 8, -4. You're going to have to find that distance using the distance formula, where it's the change in x squared plus the change in y squared. So what's that going to be? If I go change in x is 12, let's go 20 minus 12, so that'd be 8. 8 squared is 64. Plus then, if I go 8 minus -12, 8 minus -12 would be -20, or positive 20. Square that, I get 400. So you get square root of 464. Okay. Now I'm going to do the same thing for A to B. So that distance will be, subtract the x's, so it'd be 4 squared ends up being 16. 6 minus -4 would be 10, so I'll add, essentially add 6 and 4, get 10. Square that, you get 100. So now you get 116 underneath the square root. Now you don't see these two being the same, okay? But let's do this real quick. 464 divided by 4 gives me 116. Now, I know 116 is not simplified here or there, but if I could do this, I can say that 464 is root 4 times root 116. So that's 2 over root 116. So there's A prime to B prime. A to B is right there. If I divide those, 2 root 116 over 1 root 116, we get those to cancel, and it leaves me with 2. That's the scale factor that I used from A, B, C, from that triangle, to get this triangle A prime, B prime, C prime. Scale factor of 2 there. Hopefully this is helpful in addressing your homework questions. One thing I want to make sure that I reiterate, some of you, and I can tell by views, I can tell by questions, that you're just trying to attack the homework without seeing this stuff, and that's putting yourself in a bad position. Make sure you're reviewing this stuff, you're taking notes over it, looking at the other resources on my website, and that will be of great benefit to you.